We turn to summarize this course by recalling the main messages in it and pointing to topics of future research in this field. So what was this course all about? The star of this show is the Sparseland model, a concept that has been built on the vast accumulated knowledge in signal processing, math, and machine learning. This model has been taken to various applications, consistently leading to great success. Deep at the core of the Sparseland model stands the belief that the signals we operate on can be described as linear combinations of few atoms taken from a rich dictionary. We refer to the dictionary D as a matrix of size n by m, where each of its columns is an atom. When this matrix is multiplied by a sparse vector alpha, it essentially gathers few atoms from D to create the signal X. The most basic task under this model assumption is noise removal. If Y is a noisy Sparseland signal created by taking X and adding a bounded energy noise to it, our goal would be to recover X from Y, while exploiting the structure within Sparseland signals. And this brought us to meet a dear friend, the P0 epsilon problem, which seeks the sparsest alpha to explain Y as D times alpha to within an epsilon error. When denoising a signal, taking the resulting alpha and multiplying it by D should be the proposed solution. Sounds great, but when we first met P0 epsilon, let's admit it, we had some serious fears. This problem looks highly ill-posed, and it is not clear at all that it could lead to reasonable denoising. Moreover, this problem looks hopeless to solve due to the many supports in alpha that could explain why. But this first impression that P0 epsilon left on us was unjustified, and great news were discovered. We made the observation that P0 epsilon is in fact well-founded and stable, and moreover, it can be approximated very effectively by practical algorithms. Indeed, these algorithms are accompanied by theoretical guarantees for successful recovery as long as the underlying unknown is sparse enough. And if all the above is not enough, another central observation came soon after. We found out that P0 epsilon is the engine behind almost anything we might want to do in signal and image processing. And so, this problem is not only manageable, but also needed and useful. With all this background, we came enthusiastically to tackle actual applications in image processing, bringing Sparseland to them. We treated problems such as denoising, deblurring, in-painting, separation, and more. In all these algorithms, the Sparseland model stood at the center. Is it obvious how to bring Sparseland to actual image processing tasks? Sometimes it is, especially after you have seen how it is done on other closely related problems. We did see the richness in which such a combination of our model to the task can be practiced. And I conclude this summary with one final concept that accompanied us throughout this course without being explicitly stated. Sparseland is a generative model, in the sense that it defines the signal prior by proposing a machine that describes how these signals are synthesized. There are many priors, but only few of them are generative. Models, in general, are great because they give us a systematic way to design algorithms. And typically this will be highly nonlinear, so we develop this way well-justified and clearly motivated nonlinear filtering algorithms. However, when the model is generative, such as Sparseland, another terrific benefit emerges. We can now analyze the terms of success of the proposed algorithms, and this way expose weaknesses, sensitivities to some ingredients in the model or the problem, and more. We have exploited this ability mostly in the first course, but it gave us the theoretical foundations that we leaned on in this part as well.